Science Today. I'm your host, Hannah Macias, bringing you the latest in our scientific discoveries. Today's feature explores the powerful connection between electricity and magnetism, two forces that drive much of the modern world.
My name is Jaren, and I am the scientist. So in this lab, we investigated the magnetic force acting on a current-carrying wire placed inside a magnetic field. This force depends on current, wire length, magnetic field strength, and the angle between them.
And because the angle in this experiment was fixed at 90 degrees, the equation simplified as F equals ILV, revealing a direct relationship between forces and current.
This principle is fundamental to real-world technologies like electric motors, where magnetic forces convert electrical energy into motion, and devices like speakers, where electrical signals create sound through vibrating components.
This is the real-life application. Okay, so this isn't just a theory. Where do we actually see this in our everyday life?
So that's a great question. This exact concept is used in electric motors, which power appliances, fans, and even electric vehicles. It's also used in MRI machines, in medicine, where magnetic fields interact with currents to produce detailed images of the human body.
And you brought up public transportation.
Yes, so in trains, they use magnetic forces to levitate and move efficiently with minimal friction. And this lab helps us understand the physics behind all of these technologies.
Who do you know which one to take?
Is there anything on the label that's different?
Well, that one says 42, that one says 41.
So you just turned it on?
Okay, this is the procedure. We first measured the mass of the magnet assembly with no current, then we applied a -5 amps and recorded the new mass. The current was gradually increased towards zero, then reversed and increased positively while measurements were taken at each step. Each mass value was converted into force using gravity, allowing us to analyze the magnetic force acting on the wire.
So we have to go with 5.
Pull your hand here again.
This is the data and analysis. What did your data reveal?
When we graphed force versus current, we observed a linear relationship. This confirmed that force is directly proportional to current.
And what about the graph?
So the slope allowed us to calculate the magnetic field strength, B, using the relationship between force, current, and wire length.
But we didn't stop there. You tested your findings for that?
Correct. We used a different wire length and our calculated magnetic field to predict the force at a chosen current.
And how accurate would you say your prediction was?
We compared the predicted and measured values and calculated percent error to evaluate accuracy.
Discussion questions? To wrap things up, let's discuss some key questions from our experiment. In what other ways can you determine percent error?
So percent error can be determined by comparing experimental results to accepted or theoretical values from literature, or by repeating trials and calculating an average to reduce random error.
So, another question, would using different circuits significantly change the magnetic field?
No. So the magnetic field produced by the magnet itself would not significantly change. However, changing the wire length or setup measured force, since force depends on both the magnetic field and the length of the wire in that field.
Okay. So what's the biggest takeaway from this lab?
So we confirmed that magnetic force is directly proportional to current, supporting the equation F equals ILV. Our results showed a strong linear relationship, and our percent error helped us evaluate the accuracy of our measurements.
And can you tell me why those errors matter?
So they helped us understand the limitations of our experiment. Errors may come from measurement uncertainty, alignment issues, or fluctuations in current, but analyzing them improves future experiments.